remember in chapter 5, we had this, at the beginning we defined natural log, and we had this slightly absurd definition. All right, so 5.1 was about the derivative of natural log. And we had, like I said, kind of difficult definition to worry about. So we define natural log by the accumulation. It's the accumulation function of 1 over t. It's how much area 1 over t accumulates as x gets bigger. This is only valid for x bigger than t. And using this, we got a lot of neat facts. The first thing was we were able to get a pretty good picture of natural log. What does the natural log function look like? In quadrant form 1. Vertical asymptote at 0, so that was good. We figured that out. We figured out it had a
negative.
And we also said it was increasing and always concave down. The only way you can draw an increasing concave down graph is if it bends down and always gets bigger. So this is a good basic shape for the natural log graph. Goes through 1, 0. We also talked about this number e. E is about 2.72, and when you plug it into natural log, you get out 1. So E is a number that gives the area underneath 1 over t equal to 1. So we reviewed a little bit how to graph with transformations, and we talked about our log properties, which you guys kind of remember, hopefully. Log rules. Right, things like if you take natural log of a product, you get what?
Natural log A plus natural log.
Right, so you add them up. Natural log A equals natural log B. You can do the same thing for a quotient, A over B. That becomes subtraction. And then you can use this. You have an exponent rule as well. The exponent comes down the front. This is kind of our basis. Really remembering these, getting this graph, that's review. The new thing here, and the thing we really want to concentrate on, at least for a few minutes, is being able to derive natural log. Right? It's calculus, we like derivatives and integrals. So, what's the derivative of natural log x? 1 over x. All right, this is your rule. Derivative of natural log is 1 over x. So let's find the derivative of each function. A couple of these last time. If I wanted, all right, so let's find the derivative of y equals natural log of x to the 7th. Yeah. So there's two ways to do this, right? Maybe the fastest way is just going to be to use your log rule. Right? What's your log rule say you can do with this 7? Bring it in front. Right? Exponents can come in front. So this is 7 times ln x. So for the derivative, you have a constant multiple times the derivative of ln x. So it's just 7 over x. If you hate log rules, or you don't remember them, or they don't make sense to you for some reason, how else could you do this? Chain rule. Take an inside function, right? This is more complicated than x, so it's an inside function. Outside function is natural log. So to do the derivative, y prime would be the derivative of natural log is 1 over whatever's inside times the derivative of the inside. The x to the 7th and the x to the 6th leave you with 1x on the bottom. So you end up with this. How's that? Good, bad, so-so? What about root x times ln x? How would you do the derivative of this? What's my strategy here? Got to use product rule. Right? You have multiplication between two functions. Think of this as x to the 1/2 times ln x, and do the product rule. So the product rule says derivative of the first, 1/2 x to the negative 1/2, times the second, plus the first times the derivative of the second. Derivative of ln x is 1 over x. Make sense?
Mm-hmm.
Can we simplify this then? What's x to 1/2 over x?
1 over x.
Yeah, so you get, or if you subtract the exponents, you get x to the negative 1/2. Right, 1/2 minus 1 will give you x to the negative 1/2. And then you can factor out the x to the negative 1/2 pretty easily. So, I mean, I'm thinking ahead here. If I wanted to find critical numbers, I'd have to factor it out and set everything to 0. Might have to factor these derivatives sometimes. Okay. What about ln x over x? We want the derivative. Is ln x over x just ln of 1? X's cancel? No, God, no. If you do that, I will very kind-heartedly laugh at you. Because I'll think you're joking. So what do you got to do this derivative? You got to do quotient rule. There's no choice.
Is it quicker to do product?
It depends on your preference. Yeah, you can bring the x up as an x to the negative 1 and then do product rule. Doesn't matter. Let's try quotient. So the way quotient rule works, you do the derivative of the top times the bottom minus the derivative of the bottom times the top. So then you do the derivative of the bottom and multiply it by the top. And you divide everything by the bottom square. So this is nice because 1 over x times x is 1 minus ln x over x squared. So basically you're going to have to be able to do all of your old differentiation rules just with a new formula now, right? With a new derivative, 1 over x.
It wouldn't be plus.
y.
Do the derivative of the bottom.
So the derivative of the bottom is x.
What would it be? Oh, never mind.
If you do product rule, then you have a -1 to worry about.
Sorry.
But if you don't do product rule, no, you don't have to worry about any signs. What about this guy? How would you do the derivative here? Yeah, I would definitely change this to subtraction. Right, your log rule says if you have ln of a quotient, you can rewrite it as natural log of the top minus natural log of the bottom. And then the derivative is almost trivial, right? The derivative of ln x is 1 over x. What's the derivative of ln x plus 1? 1 over x plus 1. Right, the way you derive natural log is you do 1 over whatever's inside times the derivative of the inside. But the derivative of the inside here is just 1. So this is one method. So once again, say that you just don't like your log rules, or you don't remember them, or you didn't think to use them. How would you derive this without log rules?
Chain rule, then quotient rule.
Yeah. So to do the derivative of ln x over x plus 1 without any log rules, for whatever reason, you're a masochist, you would do 1 over the inside. Like, that's not too bad, that's just going to fit. But then you'd have to multiply by the derivative of the inside. That's what quotient rule, or that's what chain rule says. And to do the derivative of the inside, you have to do quotient. So the derivative of the inside here looks like what? So you'd have to do derivative of the top, which is 1, times the bottom, minus the derivative of the bottom, which is 1, times the top, over the bottom square. Okay, so I kind of like these to be equal, right? Otherwise, something's going wrong in the world. So kind of simplify this. Let me flip this guy up. Go ahead and subtract here on the top. You have x plus 1 minus x. So what should I have altogether on the top? Which is 1. X plus 1 minus x is equal to 1. Okay. Then I can cancel a little bit, right? X plus 1 on top, x plus 1 on bottom go away, and I end up with 1 over x times x plus 1. How are these the same? They're not? What would you have to do to make this look like this? Common denominator. Or if you get a common denominator and add these, you hopefully will get this. Right, if you hit this with an x plus 1, x plus 1, you hit this with an x and an x, then you would get x plus 1 over x times x plus 1 minus x over x times x plus 1. The x's cancel and leave you with just 1 over x times x plus 1. So that is the last time I will do it the long way. I wanted to do it once to show you that you do get the same thing and to show you that this is definitely more work. But unless I'm like drunk or something, I will always apply my log rules first, just to save myself some time. Okay. See if I can make it slightly more interesting. What about natural log of x? Yeah, so to do the derivative of natural log, you have an outside and an inside function here. Here's your outside. This whole thing initially will be your inside. So the derivative of natural log will be 1 over whatever's inside. So I focus on this guy first, and I do 1 over whatever's inside. And then I multiply by the derivative of the inside, which is the derivative of ln x, which is right. So at the end of the day, I end up with 1 over x ln x. Right? Right. Cool. So what are we missing so far? We've done quotient rules, we've done product rules, we've done ln's inside of ln's. What haven't we done? ln to the ln, okay. We don't know how to do that yet. That's a good one though. We haven't done any trig functions. Oh my god. What's up, guys? Should be dying to see some trig functions. Derivative of natural log of cos x. Derivative of natural log is always 1 over whatever's inside. So if I do this derivative, I'll start with 1 over cos, and then I multiply by what? Negative sine, multiply by the derivative of the inside. So I'll multiply by negative sine x, which altogether comes to what? Negative tan. Oh, is that cool? That's very amazing. You should be like knocked out of your seats. I'm surprised so many of you are still conscious.
So if you do the integral.
Yeah, that tells you what the integral of tangent is. We didn't know the integral of tangent before this. We only knew 6 trig integrals, and the integral of tangent wasn't one of them. But now we know the integral of tangent. The integral of tan x dx should equal what?
Ln cos x.
So if you integrate the derivative, you're going to go back to the original. So integrating tangent will bring you back to ln cos x. But watch out for this negative. If I integrate negative tangent, I get ln cos x. If I integrate regular tangent, you get negative ln cos x. So actually using natural log, we can get the derivative or the integral of all of our trig functions. We had sine and cosine, and then we had obscure things like secant squared and secant tangent. But now we can get the integral for tan x, the integral for cotan x, secant x, and cosine x. So that's cool to me. What about natural log? So I'll make my function natural log of secant x plus tangent x. So how does my derivative work here? Y prime equals 1 over the inside, 1 over secant x plus tangent x, times the derivative of the inside. So what's the derivative of the inside? What's the derivative of secant? Secant x tan x. Derivative of secant can't be secant squared. That would be too easy. But the derivative of secant is secant x tan x. The derivative of tangent, though, is secant squared. What's that? How does that make us feel? Angry? Sad? Depressed? Yeah, we can factor on top here. There's a secant in both terms. So on the top, factor out a secant, and you're left with a tan x plus secant x, which is exactly the same as what's on the bottom. So your derivative simplifies to just secant x. Give us another integral. Woo! We're on a roll with these integrals. So I found out from the last problem that tan x, the integral is ln of cosine, or negative ln of cosine. What's my integral of secant going to be? Well, the integral is going to get rid of the derivative and bring you back to the original function here. Natural log of secant x plus tangent x plus So I'll write out all the trig integrals in the next section. That's where they put them in the book. But this is how you get the integrals for the other 4 trig functions, is because they're derivatives of particular natural log. Easy enough? Yeah. I got one more. One more derivative. Let me go over here. This one's kind of slightly tricky. Let's do the derivative of, what is this, h? Let's let our function equal natural log of absolute value of x. So normally, natural log of x is defined only for x greater than 0. But natural log of absolute value of x is defined everywhere except x equals 0. You can put negative numbers in here, basically. Because if you put a negative 2 in, you'll do absolute value, and you get positive 2, then you'll do natural log.
So do we do the natural log of negative x plus the natural log of positive x?
So,
Something like that?
whoa, slow down the turbo. So this guy, first of all, is defined everywhere except at x equals 0. So x can equal 0. But everything else is good. Right? Now, the second thing, I feel the most straightforward way to do this derivative is to break it down into 2 cases. Right? ln absolute value of x is going to be 2 different things. Right? If x is positive, what does the absolute value do? Squat. Don't even need it. Right? So if x is positive, this is just ln x. If x is negative, what's the absolute value do? Changes the sign, right? So the absolute value is going to have to change the sign, which means you put a negative in front of the x. Right? If x is negative, like negative 2, if you plug it in here, the negative 2 will get multiplied by the negative and become positive. So our derivative for natural log of absolute value x has to be done in 2 different segments. So in order to do y prime, I'm going to have 2 different I have two different answers. I'll do the derivative of natural log x for the top branch, which is 1 over x. What about on the bottom? What's the derivative of natural log of negative x? So the derivative of natural log of anything, just take 1 over what's inside. But then what do you have to multiply by? Derivative of the inside, which is?
Same thing.
So the negative and the negative cancel and you get 1 over x. So actually the derivative of natural log of absolute value x is 1 over x as well.
And that's just because the domain restrictions.
That's just because.
The domain restriction thing.
No, it's because we got the same thing.
Well, yeah.
You meant something more than that.
Never mind.
So let me draw you a picture because this is kind of strange, right? Because this is technically a different function. Right? ln of absolute value x is different than ln x. ln x we know and love. It's our favorite function this week. Looks like this. But what ln absolute value x has two pieces, we said. There's a positive piece, and then there's what happens on the negative side. So what am I going to draw over here? It's going to end up being reflected, right? So for example, if you plug in -1 to ln absolute value x, you get out 0. If you plug in negative e to ln absolute value x, the negative goes away and you get 1 ln e. So this green guy is ln x, but both of these guys are ln absolute value x. The green guy along with the purple guy.
That makes sense.
Now, what does this mean about the slope? So over here, the slope, what's the slope at 1 of ln x?
It's positive.
1 over x, right, which is 1 over 1. Like the slope for ln x, y prime, is always 1 over x. So here, at x equals 1, the slope is 1. Now over here, the slope isn't 1 again.
It's negative.
It's -1, right, because 1 over x would be negative 1.
So the slope on the negative side is always going to be negative. Because
But it follows the same fraction. It's always going to be 1 over whatever that negative number is, because it's just a reflection. This is gonna come back in the next section, right? The fact that y prime is 1 over x here gives me an integration factor. So I calculated y prime equal to 1 over x. We calculated that. So then what can I say about the integral of 1 over x? Now, you might think it's just ln x, right? Which is true, but it's not as good as you can do. Right? The integral of 1 over x is ln x if you want to restrict your domain to x positive.
but it's also negative x.
Right, but if you want the most general integral here on the largest domain, you put ln absolute value. Right, so this is true for all x except x equals 0. If you take off the absolute values, it's only true for positive x. So the most general antiderivative of 1 over x is ln absolute value x. We'll use that in the next section. So you can do derivatives of ln x or not. What you want to be aware of is now I can basically ask you anything that I asked you in the first 4 chapters, but I can put an ln in. Okay? So for example, you should now be able to do something like find the equation of the tangent line to y equals natural log of x to the 3/2 at 1, 0. So find the equation of the tangent line is something we did in chapter 2, I think. But now you're going to have to do it again with natural logs to make sure you understand that it's all the same garbage. But it's good because it's good review. How do you actually find the equation of a tangent line? Yeah, so for the equation of the tangent line, you need 2 things. You need a point and a slope. We have a point. We have a point, so we need a slope. To find the slope of a curve, you do the derivative. Okay, so to find the equation of the tangent line, we have the point, we look for the slope. What's y prime going to equal in this case? 3 over 2x. Right? I mean, either you do your chain rule, or you use your log rule to write this as 3/2 ln x. Then there's a constant multiple of 3/2, and the derivative of ln x is 1 over x. But I don't actually care about the entire derivative. I just want the tangent line at 1, 0. So I have to plug in 1. So y prime evaluated at 1, x equals 1 will be 3x. The historical law needs evaluated. So there's my slope. M equals 3x. I have a point, I have a slope. So do your equation of the line. Y minus y1 equals m times x minus x. Y minus 0 equals 3/2 times x minus 1. Y equals 3/2 x. So even though it's a new function, ln x to the 3/2, because the derivative is so nice, so simple, it actually worked out to be a pretty straightforward slope, straightforward problem. Area under the curve always sucks. One more example. Find all relative extrema for the function y equals 2x minus ln. So how do I find relative extrema? Take derivative, find critical numbers, and then do your first derivative test. Which hopefully you vaguely recall. So do the derivative first. Y prime equals derivative of 2x, just 2, minus derivative natural log 2x, 1 over 2x times 2. Yeah, so just 1 over x. And because I'm trying to find critical numbers, let me go ahead and make this one fraction. Then I can do the top equal to 0 and the bottom equal to 0. Question?
So, like that, if there's a log, natural log of any x multiplied by a constant is going to be the same
Yep.
thing.
Yep. Wait, constant's going to be the same thing?
Or it's going to be the same
It's
thing.
going to be 1 over x. The derivative is always 1 over x. Yeah, because
That's what I meant.
natural log of a constant times x is equal to natural log of a constant plus natural log of x. So this is just a vertical shift, really. It goes to 0 when you derive. So, and then this goes to 1 over x. Yep, so if there's just a constant times x, the derivative will be 1 over x. Well, let's go ahead and get a one fraction here. So I'll multiply by x on top and x on bottom, right? X over x. So y prime is 2x minus 1 over x. How do I find my critical numbers? Top and bottom is 0, right? Undefined and when it actually equals 0. So I'll have to do 2x minus 1 equals 0, x equals 0. X equals 1/2 when you solve, and x equals 0. These are my critical numbers. So then, since I'm trying to find relative extrema, I'm going to do my first derivative test and see if I have maxes or minis. I need to test between and beyond 0 and 1/2. Now, do I actually need to test to the left of 0? No, why not?
Because it's natural log.
It's not in the domain of your function. Your original function cannot have x less than 0. It's got a vertical asymptote of 0. So I already know this guy is a vertical asymptote because of this. But I do need to test on either side of 1/2. So I'll plug in 1/4, I guess. Good as anything. Oh, actually, I could probably do 1 over e squared or something. That'd be smarter. Oh, wait, no, I don't have natural log. 1/4 is good. And then 1. I just pick something on the left and something on the right. When you put 1/4 in the top, 2 times 1/4 minus 1, 1/2 minus 1, that's negative. Over 1/4, positive. So you should get negative. When you put 1 in, 2 times 1 is 2 minus 1, that's still positive. So when you put 1 in, it turns back to positive. So my function goes down, right, decreasing, then increasing. So I have a relative min there. And what is the relative minimum? 1/2. Relative min. My x value is 1/2. My y value comes from plugging 1/2 into the original function. So 1 minus ln of 1